Hello folks. Today it's a part of a formal lecture for class, and thinking that it will be useful for all people. So I will upload this thing into YouTube as well. The topic for my discussion today is about magnetism. Especially today's description will be mainly focused on the origin of magnetism. As you know that magnetism as a term means something that attracts other substances, especially made of iron in old days. In China, they used to have certain ores of iron, which they didn't know at that time, which they used to attract other things, especially coins. In those days, coins were made of iron as well. So they thought that that stone attracts money, since coins were made of iron. And they used to worship it. Then in several other countries also, they started to take notice of such properties. And as knowledge started to spread, people started to know that anything that is of such property faces north-south. That property can be transferred to others by stroking like this, and so on. But nobody knew how that happened. Now, with advancement of theories, we have got some idea about magnetism. So, electricity and magnetism are both caused due to charge. So, if we have got charged bodies, electricity can exist and magnetism can exist. If there is no charge, no movement of charge, or no charge overall, then both of them do not exist. Though that is not the only condition, there should be sometimes we have to have a movement, balanced movement, imbalanced movement, and so on. So regarding magnetism, so let us just at least write the topic first. It is magnetic field or magnetism, let me say. So magnetism is basically due to rotation of charge, rotation or revolution of charge. So let us take a very good example of a typhoon, let us say. So in a typhoon, what happens is the storm is brewing like this, so it will displace certain things in this manner, centrifugal tendencies. But at the very center, what happens is at the nucleus, let us say, at the very focus, let us say. So when the velocity of this thing increases very much, things here are lifted up. And then thrown haphazardly. So that means that there's a certain sort of force. So there's a vertical force. Things are moving like this, but there's a vertical force. And maybe the force is also in downward direction, but that is not properly visible to the camera or the people, but this force is visible. So that means if something moves like this, there is some sort of this force in a perpendicular direction to the axis of the circle, plane of the circle. And similarly, in whirlpool also, same thing happens. So there's a movement of air like this, and the dust particles or paper get lifted like this and then thrown away. So the same thing applies to electricity or charge as well. Now, so let's go through something about Earth. This is Earth. Earth rotates around its axis, and there is some sort of magnetic field here in this direction. So what happens? Is it because of iron or nickel or something like that? No, it's not, because the iron of the surface, yes, they exist in solid state, but the iron of the core, they are in a plasma state, not liquid, not gas. It's so hot there, and at such high temperature magnetism does not exist, which has been proven scientifically. Above that Curie temperature or Curie point, magnetism does not exist. Or let us say distinct magnetism doesn't exist, paramagnetism does not exist. So what is happening here? The thing happening here is that this magnetism is because of the charge revolving or rotating along with Earth. The charge is rotating or revolving along with Earth. And some theorists often state that it's because of the charge currents that develop in the core as well. So in the core, lots of charges distributions are there, some type of storms or winds are there, and because of those storms or winds, there is magnetic field like this. So let us verify it in some other way as well. When we have a circular coil like this, and the current is flowing like this. So this is current going and going out. And here we have magnetic field in this direction. And when this thing extends, when I extend it like this, so circular coil extending like this, like this, like this, like this, like this, like this. It's a solenoid. And we have a magnetic field in this direction. Everybody knows. At your age level, everybody knows. So because you studied about solenoid in class 9 or 10, you even studied how to increase their magnetic field by increasing current, by increasing the number of turns, by decreasing the diameter, and so on. So here also we have got magnetic field. Here also we have got magnetic field. And next is in atoms, the nucleus is there, electrons are revolving like this, and they create certain magnetic field here. Not only that, even the rotation of several particles around their axis themselves develop some sort of molecular or atomic or subatomic magnetism. So that means magnetism is caused due to the rotation or revolution of charged particles. So static charged particles, they don't give magnetism. If they rotate, they give magnetism or magnetic field. So lots of examples to show that. So flow of charge gives electricity, current, but rotation or revolution of charge gives rise to magnetic fields. So with the Earth's magnetic field, it is started to magnetize a lot of other things. There are natural magnets. Now with this technique, solenoid technique, people obtained a lot of other type of magnets, and with time lots of techniques developed, and nowadays magnetism is magnetization is done by adiabatic cooling or so on, lots of those things. So this is magnetism. Now the influence of magnetism is seen in the form of fields, just like electric fields there. So we have got area up to which magnetic field is seen, that is the magnetic field, and we have the strength of magnetic field, electric magnetic field strength, let us say, just like electric field strength, and we have got flux lines or field lines, just like in electricity. So the field lines of magnetism, are thought to be almost same as that of electricity. So what happens is, if I have a bar magnet here, then its field lines will be somewhat like this. So if it is the N pole and if it is S pole. So people got idea about this magnetic field by using compass needles, by using iron dust sprinkled on paper. They just sprinkle something on paper, they put magnet down and they tapped it like this, and they arrange beautifully into certain shapes. So the shape would be somewhat like this. So at the very center, this thing is symmetrical. It goes straight like this at the very center. Then at the edge, it goes somewhat like this. So from N it goes, and then it starts to be attracted to the south. So and this will go somewhat like this inside the magnet. It goes like this. Then let me draw a few more lines. So these are two more lines here. So one line will go like this, and then it goes like this. So as I repeat, they have been drawn by using either magnetic iron particles or by the use of compass needles. So like this, and then one more here. So it goes beyond the reach of the diagram, somewhat like this. So one of the most common type of magnetic field is because of this bar magnet, and the same thing goes to this side as well. So I often encourage students to complete this diagram by drawing this side as well symmetrically. Let me repeat it, symmetrically. So here it might not be possible in this short video, but in class they have to do like this. So here outside the field lines will be from N to S, but inside it will be from S to N. So outside N to S, and inside it is S to N, something to be taken care of. So this is bar magnet. And if we have got a horseshoe magnet, Horseshoe magnet, you might know it's a magnet shaped like a horseshoe, and a horseshoe is not like our shoe, you know it very well, I suppose. It is certain U-shaped iron structure used as a shoe of horse, which is fused into the hoof of horses, so that their hoofs do not degrade or do not erode during long travels. So it will be iron which erodes and not hoof, and that iron goes for a long time. So it is just a fuse. They make it red hot, hoof of the horse, and they just fuse it like this. It melts the hoof to a certain distance, and it does not give pain to the horse. So animal activities might say it's a trouble for the horse. No. So it doesn't give pain to the horse. Just it is fixed somewhere in middle. It doesn't touch their sensory organs, let us say. So we have got a horseshoe magnet, somewhat like this. So let's say it shape be like this. It will be U shape. It will be U shape. So this is a horseshoe magnet. So my board is not so smooth enough. I got it done from our local carpenter, a good friend of ours as well, and he is not an expert in constructing boards, so that's why it is slightly rough. You can see from there also. You can see brightness at several locations, and less brightness at other locations. So if I have got this N and this S, so what will be the field lines look like? So first, let us say from N it comes. From N it protrudes outward. It tries to spread, but ultimately it has to go here. From N it comes. It tries to spread, but it has to go here. From here it tries to spread, but is pulled to this S. From here it tries to go perpendicularly, but it is immediately pulled like this. And again from here tries to go out, but pulled like this. And from here also same thing, tries to go out but is pulled. And from here tries to go out, but it goes here, comes like this, and then it comes like this. So then lots of these things. So like this. So this is the field lines due to a horseshoe magnet. So looks like something like a hair cell like this. So then we have a solenoid. So a solenoid will be somewhat like this. So what I often do in class is, I first draw two guides like this, guidelines, let us say. I don't have this long scale with me, so I'll use this steel bar. And fortunately, I don't take this to class. It is mine, not of college. some part of a steel furniture which I use. So let me say this is the guideline for the solenoid. So I am drawing this to draw the outer border of the solenoid, because otherwise my border would go very, very uneven. So let me draw the solenoid. So this is the solenoid. See, with that line, it has given me a very good disciplined type of turns. I do the same approach in class as well, and then later on I rub it. So let me rub it like this. So let me rub it like this. So I did not use duster to rub it like this, because duster does not give me this much of fineness or precision as your fingers. So this is a solenoid, and current is flowing in it. And now in a solenoid, what happens is, in each turn, if I say the turns like this turn would be towards you, this turn would be away from you. So the part of this turn will appear larger to you, and this turn would appear smaller to you. So that's why I have to make some arrangements here. Let me show it this portion a bit thicker. a bit thicker, this portion a bit thicker, this portion a bit thicker, this portion a bit thicker, and so on. So we have to do this for the whole of these things. Now let me draw the field lines. The central one will be the most symmetrical. It goes straight. So let me draw this. So on this board, I am not able to draw it fully straight because I am not as comfortable as in college. So in college it's a habit, but here it has not been my habit yet. And the boards of college are very smooth. They are professionals, but here it's not so. Now, so let me draw a few more lines here. 1, 2, and then 3. So this line will come like this, outside. Like this. So this line will be like this. And this line will be incomplete for this board. So like this. And like this. So this is the magnetic field due to a solenoid. And if I draw it here, it will be the same familiar shape of the bar magnet, pear shape, let us say, or let us say half of the apple, let us say. Now what happens is, let me say the current is flowing in this direction. Current coming in this direction, this direction, this direction, this direction. So let me draw this. Coming in this direction, let me draw this. Thicker, this direction. Let me draw this. This direction, let me draw this. This direction. This direction. This direction. So what happened is, current is coming like this. Current is coming like this. Coming like this. Now if so, if I look from here, current coming like this, coming like this. If I look from here, let's say current flowing like this, and if I look from above, it will be clockwise. It will be something going from like this is clockwise. So clockwise means that there will be south pole here. So you must have studied this in some class. So in a solenoid, when you look at from certain side, if it is clockwise, there will be south pole. And when you are looking from one side, if it is anti-clockwise, it's north pole. So it is moving like this. So moving like this. I look from here. I look from here. I look from here. So let's like this. When I look like this, it is anti-clockwise. You can try. Anti-clockwise. So this is N pole. So N means that now the magnetic field will be somewhat like this. It will be coming like this, like this, like this, and inside it will be like this. So these are some of the field lines. So we can draw the same type of field lines to other things as well. So this is just a preliminary practice. You have to do for this side also. You can make it asymmetrical. Should be symmetrical, let us say. So you can draw the same thing to others as well. And with that, we'll be able to go for further courses or further lessons, especially the effect of magnetic field on a current carrying conductor. Because a current carrying conductor also has got magnetic field, and when it is inside another magnetic field, several interactions happen, and that gives us certain sort of effects, certain laws, certain tools, which is the foundation of a lot of machinery inventions, which have been very much advantageous to we people.